Alright, so in this video, let's look at the last major way of improving performance of a Rankine cycle, which is through regeneration. So the idea here is that I can improve the thermal efficiency by using the energy that's in the material that leaves the turbine to preheat the material that enters the boiler. Okay, now this will lower the heat required in the boiler, which should increase thermal efficiency. This is actually a very commonly used process in a lot of different power plants around the U.S. Or the world, but it's going to add some complications. So there are two main ways that this is done. One is the open feedwater heater. And in that one, what we're going to do is we're going to bleed some material out of the turbine at an intermediate pressure, so a little bit early, not all of it, just some. And we're going to mix it with the material going into the boiler. But now the problem here is that I have to match the pressures. If I take it out at some pressure that is higher than the low pressure, then it's going to need to be combined with something at the same pressure, or I can't get them to mix. Okay, it's a physical limitation. You'll learn more about that in a fluid mechanics course if you haven't already. If I say, well, then why not just take it out at the end? It'll be at a low pressure. Well, then what I have to match is the material coming out of the condenser. And at that point, then I would have a saturated liquid vapor mixture going into a pump. And now that's going to cause cavitation inside the pump and destroy the pump. So I can't do that. So I need to go to a higher pressure than my minimum, but I don't want to wait too long. So this is going to cause a little bit of complication. I've got to match those pressures, which means I'm going to need an extra pump as a minimum. Now there's also a closed feedwater heater. This one just says, okay, I'm going to take some of this material out. I'm going to run it through a heat exchanger, closed pipes, so I don't have any real substantial pressure loss across there. And then I can use it again back into the turbine. I could blend it into the condenser. I've got all sorts of options at this stage. And then I'm going to take that, and the opposite side of the heat exchanger is going to be the material going into the boiler. So if we look at these as pictures, because it's a little hard to understand the words, this is what a typical open feedwater heater application would look like. So, well, let me start here. Okay, I'm going to pump the stuff up to a high pressure and then feed it into the boiler. And this could superheat it. As we've seen, that's probably my best bet. Or maybe just take it to a saturated vapor. This is then going to go into my turbine, which will go into the condenser and back through the process. But now this is where it gets a little complicated. I'm going to take it, part of it, not all of it, part of it, out of the turbine early. I'm going to feed it into an open feedwater heater, which is really a mixer. I mean, literally, this can look like a T in a pipe. Okay, one stream coming in here that's at high temperature, one coming in here that's a low temperature, so that they exit, making a blended stream, still liquid, but hotter than it was before, going into my second pump. This pressure here can range anywhere between the low pressure and the high pressure, and the exact amount I need is going to be whatever will create a saturated liquid to go into this pump here. Again, I'm trying to maximize my use of energy, but I want to guarantee that I don't damage my pump. So I want this to have a quality of 0 here. Now I still am going to send most of it through the rest of the turbine and into the condenser and into a low pressure pump with a quality of 0 at the low pressure. And then that's going to come over here. And it's going to be my second stream into the open feedwater heater. Now, one of the things that's going to make this a little bit trickier is I'm going to have to analyze my turbine a little bit differently, and I'm going to have to now add an analysis of this open feedwater heater. Let's talk our way through that. I'm not going to write down equations yet, I'm going to save that until class next time, but I want to talk about it so as I write these equations down in lecture, it'll make sense to you. So the turbine, if you go back to your first law, remember I had the option of I could have one stream in and one stream out, which is what we've been doing, or I could have multiple streams in and out. Well, this time I have one stream in and two streams out. Okay, this is power production, so that's not a material stream, that's energy. So one in and two out. So when instead of just looking at enthalpy in minus enthalpy out, I'm going to look at the mass flow rate times enthalpy in here, minus the mass flow rate times enthalpy out here, minus the mass flow rate times enthalpy out here. So why am I having to include mass flow rate? Because the mass flow rate is not the same everywhere. I can't just divide it out like I did before. It won't cancel. So that's going to be one little extra complication that I have. Now, how am I going to know how much energy is going to flow in each of these things? Well, that's where the analysis of the open feedwater heater comes into play. This one has two streams in and one stream out. So in this case, it's streams 2, 5 in, and 6 is out. Now, the open feedwater heater, I said, is likely to be really as simple as a T in a pipe. So there are no moving parts. There's going to be no work. My job is to add energy into the stream, so I should have this very well insulated, so Q equals 0 is reasonable. I don't expect to have much significant kinetic or potential energy change. So in general, the sum of the mass times enthalpy in equals the mass times enthalpy out. And that will actually allow me to solve for the mass flow rates in the various streams. If I know one, I can figure out the others. If I don't know any of them, then I could maybe say that the stream coming out here and that's going to come on through here, that's 100% of the flow. I'm going to have splits here, so I could say 100% is Y, and therefore this is 100% minus Y. Okay? So Y plus 100% minus Y will add up to give me that 100%. And that way I can have a fraction of flow, not necessarily a specific flow rate. Now, if we wanted to look at a closed feedwater heater, this can be configured a lot of different ways, but certainly one way is shown here. The simple thing is it only requires one pump. Okay? But what I'm going to do is I'm going to take the material, pump it up to a high pressure. So it's going to be saturated liquid coming into the pump, compressed liquid coming out. But I'm going to preheat it first using some of the material out of the turbine. And then I'm going to send the rest into the steam generator to come out as either saturated or superheated vapor, which will go into the turbine and turn the blades and produce power. But I can extract some of it early and send it to do the preheating. And then I'm going to run that into the condenser. And in the process of running it to the condenser, it's kind of a piping nightmare, but otherwise the analysis simply is that my condenser has two inlet streams, one outlet stream. This one will stay in a little longer because it's going to be at a slightly higher energy, and I will then need it to lower its pressure, but I can do that through blending. Okay, so there's various ways this can be done, but I can analyze this. I still have the same thing, one stream in, two streams out, so I can do MH in minus MH here minus MH here. That will produce the work of the turbine or power of the turbine. I can analyze this because on a heat exchanger, I can analyze that the heat into the system here is the heat out of the system here. Those two are equal to each other, opposite signs, so the net amount of heat transfer is 0. Again, no moving parts, so the net work is 0. And so I can analyze here exactly what my flow rates need to be. So all my processes are really the same, except for I'm adding in some sort of heat transfer device that's a little bit different. And now I'm going to need to figure in mass flow rates. So we'll be looking at that in class this week.